We're going to continue our discussion of carbon nucleophiles with Wittig reactions. So the Wittig reaction is an important reaction in organic chemistry. It allows us to modify the carbon skeleton, and whenever we encounter reactions like this, we always make a big deal about it because of how important it is in synthesis. Essentially what happens in the Wittig reaction is we convert an aldehyde or a ketone into a new carbon-carbon double bond. And it doesn't just have to be a CH2 group. We can have other alkyl groups and other groups coming off of the carbon atom. So the Wittig reagent that we're adding to the aldehyde or ketone is an example of a phosphorus ylide. And an ylide is a neutral compound that contains a negative charge and a positive charge on adjacent atoms. We can draw these two different resonance contributors for this phosphorus ylide, but it turns out this first resonance contributor that has the negative charge on the carbon and the positive charge on the phosphorus is actually the most significant resonance contributor. And so this negative charge on the carbon makes it a good nucleophile. The Wittig reaction is an example of a 2+2 cycloaddition. The Diels-Alder reaction that we studied earlier in the semester is an example of a 4+2 addition. Again, where this nomenclature comes from, the 2+2, we have two conjugated pi systems, one on each reagent that are involved in the reaction, and then the 2 tells us how many atoms on each compound are involved in the pi system. So we've got 2 atoms involved in the pi system on the aldehyde or the ketone. And then in the other resonance structure, we have the double bond between the carbon and the phosphorus. So we have 2 atoms involved in the conjugated pi system in the Wittig reagent. So in this mechanism, the pi bond on the aldehyde or the ketone attacks the phosphorus, and then the lone pair on the carb anion attacks the carbon of the carbonyl group. This gives us this 4-membered cyclic intermediate. And then in the final step, we essentially exchange the oxygen for the carbon to give us the carbon-carbon double bond as opposed to the carbon-oxygen double bond that we started with. The synthesis of these Wittig reagents is a 2-step process, and the starting material is an alkyl halide. The first step is an SN2 reaction, so this phosphorus phenyl group is acting as the nucleophile, and then the halogen is acting as a leaving group. And then to deprotonate this phosphonium salt, we need a strong base. In this case, we used a butyl ion with the lithium counter ion, but a variety of strong bases could have been used in this second step. Sodium hydride or sodium amide would have been good alternate choices for this strong base. So we've talked about the reason we're so interested in the Wittig reaction is because it allows us to modify the carbon skeleton. Plus, we're adding an alkene, which we know gives us a lot of synthetic opportunities. Enhancing its usefulness in synthesis is the fact that the Wittig reaction is stereoselective. So here's our starting aldehyde. We have the big bulky phenyl group on one side, we have the hydrogen on the other. And then this is our Wittig reagent. This is the carbon that's going to be taking the place of the oxygen, and so it has a methyl group and a hydrogen. And so we'll have a methyl group and a hydrogen attached to the carbon that we added during the process of the Wittig reaction. And if the Wittig reagent was derived from a simple alkyl halide, then we'll get the Z-alkene as the major product. So the bulky phenyl group on our starting aldehyde ended up on the same side of the double bond as the more bulky methyl group in the starting material. Now, depending on the nature of the Wittig reagent, we can actually change the stereoselectivity. So on the last slide, we saw that in the Wittig reagent, if we just have alkyl groups coming off of the carbon that we're adding, we're going to get the Z-alkene as a major product. If instead we have electron withdrawing groups on the carbon that's going to be installed, then we'll actually get the E-alkene as the major product. Also, if we have a benzene ring coming off the Wittig reagent, doesn't matter what's going on in the aldehyde or the ketone, that will also give us the E-alkene as the major product. In the E-alkene, the major bulky groups are on opposite sides of the double bond. Now, we're not going to go into detail as to why this changes the stereoselectivity, but I do want to point out that the electron withdrawing group or the benzene ring stabilizes the negative charge in the Wittig reagent, and therefore these Wittig reagents that have either electron withdrawing groups or benzene rings, they're called specifically stabilized Wittig reagents. Okay, I don't want to spend too much time on this slide, but the book mentions these Horner-Wadsworth-Emmons reactions, or HWE reactions, and you may see it in some of the examples in the book, so I at least wanted to mention it. These reactions employ a reagent very similar to the stabilized Wittig reagent, and so it also yields E-alkenes as the major products. This is our stabilized Wittig reagent with an electron withdrawing group. This is the HWE reagent, so rather than having 3 phenyl groups, we've got this double bond to the oxygen and these methoxy groups. And so, like I said, if you see this as opposed to the Wittig reagent, again, the negative carbon is the one that we're adding, and so this has a hydrogen and this ester. So in our product, we get the hydrogen and the ester, and we get the E stereoselectivity. When we use the Wittig reagent in synthesis, there's generally 2 routes for making the desired alkene. We can either do it where this side came from the aldehyde or the ketone, and this side came from the Wittig reagent, or vice versa. And so to determine which route is better, we want to consider what alkyl halide we would need to make the different Wittig reagents, remembering that this starts with an SN2 process. So the alkyl halide that I would need to make this Wittig reagent would be a methyl alkyl halide, whereas the Wittig reagent I would need, or the alkyl halide I would need to make this Wittig reagent would be a secondary alkyl halide. So again, these are the 2 alkyl halides that we would need to make the respective Wittig reagents. Because this first step is an SN2 process, we know that's much easier with a methyl halide as opposed to a secondary halide. So the best choice would be to make this Wittig reagent and then use this as the ketone. And so the overall synthesis for this alkene would be to start with a methyl halide, convert that into the Wittig reagent, then react that with the necessary ketone to give us the alkene that we desired.